Hey kiddos! Well, today we're going to talk about a concept that you guys are all familiar with, and that's Pythagorean theorem. And then we're going to talk about something that's a little bit new, which is sohcahtoa. Okay, so we're going into trig. So, Pythagorean theorem. In a right triangle, the sum of the squares of the lengths of the legs is equal to the square of the length of the hypotenuse. So in the picture that we have here, this is my right triangle. As you can see, it's noted by this symbol here. A is considered a leg, B is also considered a leg, and C is the hypotenuse because it is the longest side, which you will always find located across from the 90 degree. Okay, so essentially, if we were to take a squared and add it to b squared, it would then equal our c squared. So let's look at a few examples. All right, so in our first example, we have a is 4, b is 5, and our c value is x. Okay, notice you should always be able to identify the c first because that's always going to be across our 90 degrees. A and B can be interchangeable, so don't freak out about, oh, which one's actually A. So A and B, you can switch them up. C is the one that has to be 100% correct. You cannot mix up the hypotenuse with anything else but C. So if we were to use A is 4 and B is 5, then we would have 4 squared plus 5 squared equals c squared. Notice I'm using Pythagorean theorem here. So if I were to work this out, 4 squared is 16 plus 5 squared, 25 equals c squared. When we add 16 plus 25, we get 41 equals c squared. Now please don't panic. That is not the final answer. You have one last step, and a lot of people forget this, but you have to take the square root. Okay? So now we end up with our c being the square root of 41. So we're probably going to end up with a decimal answer. And if we do have decimals, let's just round to the 10th. So we would end up with 6.4. So our A value was 4, B value was 5, and our C value ended up being 6.4. A way to check yourself is that your hypotenuse should always be the longest side. So if this number is not longer than the other two, then you know that there's probably something wrong. Example 2. Same concept. Notice I have A is 3. We have no idea what B is yet, but we do know our hypotenuse, which is C. So when we plug it into our Pythagorean theorem, we end up with 3 squared plus B squared equals 7 squared. So let's go ahead and simplify, and we're solving for B. So 3 squared, 3 times 3 is 9, plus B squared equals 7 squared, 7 times 7, 49. Remember, we're solving for B here, so I'm going to have to subtract 9 to both sides. You end up with B squared equals, that canceled out, 49 minus 9 is 40. Now to get B by itself, last step is to take the square root. And if I take the square root of 40, we end up with a B value, and it's a decimal, and it is 6.3. So that is 6.3. All right, so let's look at the converse of Pythagorean theorem. States that if the sum of the squares of the lengths of the two shortest sides of a triangle equals the square of the length of the longest side, then it actually is considered a right triangle, which means it would have that 90 degree. So for example, let's say you have no picture, you're not sure if there's a 90 degree or not. How can we justify that this is in fact a right triangle? Well, simply we're going to just plug it into Pythagorean theorem. A would be 8, B would be 15, and C would have to be 16 because 16 is the longest side. So if we were to do 8 squared plus 15 squared, we should get 16 squared. So let me just plug that into my handy dandy calculator. 8 squared 64 plus 15 squared, 225 equals 16 squared, which is 256. So 225 plus 64 is 289, which clearly you can tell is not equal to 256. So therefore, this example is not a right triangle. So for the next example, notice the only thing that we're changing here is our hypotenuse is now 17. So let's see if this instead will give us a right triangle. So we're plugging into Pythagorean theorem. 8 squared plus 15 squared equals 17 squared. We already know that 8 squared plus 15 squared was 289 equals 17 squared. And when I do 17 squared, I get 289. So therefore, yes, this actually is going to be a right triangle. All right, so now looking at Pythagorean inequalities theorem. So for any triangle, for example, any triangle ABC, like an example here, where C is considered the length of the longest side of the triangle, okay, then the following statements can be true. If C squared is less than A squared plus B squared. So that means if you add A squared plus B squared and that value is less than your C squared, then this triangle is going to be acute. And then the opposite would be that if C squared, let's say, is greater than the addition of A squared plus B squared, then that triangle would be considered obtuse. Pythagorean triple is when you have three whole numbers that satisfy A squared plus B squared equals C squared. So in previous examples where we ended up with decimal values, those are not considered Pythagorean triples at all. So it has to be three whole numbers in order for it to be called a Pythagorean triple. So example 5, are the following right triangles? So are they a right triangle? And if they are they actually a Pythagorean triple? So we are going to plug them into our Pythagorean theorem and see if they actually work. And if they do, then yes, they're a right triangle. And yes, because these are all whole numbers, they would be a Pythagorean triple. All right, so if we plug in 3 squared plus 4 squared equals 5 squared, remember here, make sure the biggest number, okay, is identified as the C, okay, don't mess that up. So if we work that out, we get 9 plus 16 equals 25, and 9 plus 16 is 25, so 25 equals 25. So check mark, yes, 3, 4, 5 is a Pythagorean triple, and it is a right triangle. All right, so the next one, 5, 12, 13. Notice I've already got it plugged in. So 5 squared is 25 plus 12 squared, which is 144. Equals 13 squared, 169. 25 plus 144 is 169. So therefore, check mark, that equals that is a right triangle, and it is a Pythagorean triple. All right, now let's look at a 7, 24, 25. So when I plug that in, I have 7 squared, which is 49, plus 24 squared, which is 576, equals 25 squared, which is 625. If I add 49 plus 576, eureka, I get 625. So therefore, yes, it is a right triangle, and because these three numbers are whole numbers, then yes, it is a Pythagorean triple. Now the next one, we've actually already have done 8, 15, 17. We've already proven that before, so I'll go ahead and put a check there. For the last one here, I want you to yo that problem. All right, so let's not talk about Pythagorean theorem anymore, and let's move on to sohcahtoa. So, talking about trig here, okay, and trig is going to consist of sine, cosine, and tangent. So this is why sohcahtoa is important and helpful for you to memorize, because sine is opposite over hypotenuse, OH. Cosine is adjacent over hypotenuse, AH. And tangent is tangent, opposite over adjacent, OA. Sohcahtoa. So this basically helps you remember this part right here, okay? So very important. You have to have this memorized when we are solving right triangles by trig. Now, just want to make sure that you know where to locate opposite, adjacent, and hypotenuse. Now, the easiest of them should be the hypotenuse. The hypotenuse will always 100% be across from the 90-degree angle. So you guys, by now, should not get that wrong. Now, the opposite and adjacent can always change. Now, they can always change because it's always based off of theta, or basically the angle that's given to you or the angle that you're looking for, okay? So we call theta the measure of the angle, okay? So, for example, if this is the angle that I'm in reference to, the side opposite this angle is called the opposite, and the side that's right next to it that touches the angle is known as the adjacent side. So, let us label the sides on the following 3 triangles based on the location of theta. So, this is basically you guys practicing identifying hypotenuse, where the opposite side is based on theta, and where the adjacent side is based on theta. Now, if you want a shorthand, because I know you guys don't like writing out all those words, you can use H for hypotenuse, O for opposite, and A for adjacent. So, let's look at the first one together. H, hypotenuse, is always easiest to find because it's across the 90 degree. Now, across the theta, which is in this angle right here, so across that theta is going to be my opposite side, which would mean then right next to theta, the side that touches the angle, is going to be my adjacent. Next one, again, always first identify your hypotenuse, because then at least you got a 50-50 chance of getting the other two right. Haha. So here's theta this time, so therefore across from theta, so the side that doesn't touch theta is going to be our opposite, and the side that actually does touch theta, which is right next to it, is our adjacent. I want you guys to do that one. Oh, yo. All right, guys, so for the next part, there is, you're going to need your calculator to do this. And the number one thing is you want to always, anytime that we're using trig, okay, anytime you plan on using sine, cosine, tangent, or anything like that, you always want to make sure that your calculator is set to the degree mode, all right? So to do that, to change it, you go to, obviously, turn your calculator on. Then you go to mode, which should be next to the second button, and you should see this screen. You're going to go down here. I think it's the third line. You should see it says 2 options, radian or degree. So you're going to click move over, use the right cursor, okay, and highlight the word degree, okay? So you want it to be with degree highlighted, okay? That is a must whenever we're using our calculator for sine, cosine, and tangent. All right, so for this final part of our notes, we're going to find the value of sine, cosine, and tangent ratios for each of the triangles. You want to make sure that you pay attention to which angle they're referencing. So notice for number 1, 2, and 3 here, they're referencing P. So notice I've already have it highlighted here because that is the theta. That is our theta, basically, okay? So when we write our fraction for sine is going to be opposite over hypotenuse. Our fraction for cosine is adjacent over hypotenuse, and our fraction for tangent is opposite over adjacent. And we actually have number values, so that's what we'll be putting here. Once we have the fraction written down, then we can transfer those into decimal form. And that's all we're pretty much doing here. Notice for the decimals, they want us around 2 places, so keep that in mind. So you do, like I said, need a calculator here. Make sure you're in degree mode already. So we're going to do 1, 2, and 3 together, 10, 11, 12, and then 13, 14, 15 together. And you all will be responsible for doing the others. So first thing that I need to do is I need to identify theta, which is P in this case, for 1, 2, and 3. And I went ahead and I identified my 3 sides. I know that this is the hypotenuse because it's across the 90 degree. Across from theta is the opposite side. And next to theta is my adjacent side. So now that I have that, it's going to make writing my fractions a lot easier. So sine of P is opposite, which is 4 over hypotenuse, which is 5. Cosine is adjacent, which is 3 over hypotenuse, which is 5. And tangent of P is opposite, which was 4, over adjacent, which is 3. So those are my fractions for sine of P, cosine of P, and tangent of P. And then the decimal versions of those are 4 over 5 is 0.8. 3 over 5 is 0.6. And 4 over 3 is 1.3 repeating. All right, so for this next problem that I'm going to do, sine, or 10, 11, and 12, we're looking for sine, cosine, and tangent of angle D, which is our theta. And this is actually a very rare type of situation because theta is your 90 degree. Okay, so we automatically know that that means this is our hypotenuse, which puts us in a dilemma of figuring out which one's opposite and adjacent. Now, it's always going to depend on the kind of situation that you come across, which you will not come across very many of these. And if we do, then I will definitely tell you guys which one's opposite and adjacent. If you notice here, these two values are actually congruent. So this is actually a special right triangle. It's a 45, 45, 90 degree. So it doesn't really matter which one I mark as opposite and adjacent because they're both the same value. So that means those two fractions are going to look the same. So sine of D is 5 over 5 square root of 2. Cosine of D is also going to be the same, 5 over 5 square root of 2. And notice here, tangent of D is actually going to be 5 over 5. So if we reduce 5 divided by 5 square root of 2, we end up with a decimal of 1.41 because I went 2 places. So notice sine and cosine are going to be the same. And 5 divided by 5 is 1. All right, and the next one here is 13, 14, 15, and that is sine of x. So notice I went ahead and labeled 25 is my hypotenuse. Across from theta, which is x in this case, because that's what we're using for 13, 14, and 15, is so 24 is going to be the opposite side, and the adjacent side, the one that's next to theta, is going to be the side with 7. That is my adjacent side. So, my fractions. Sine is opposite, 24 over hypotenuse, 25. Cosine is adjacent, 7 over hypotenuse, which is 25. And the tangent is opposite, 24 over adjacent, which is 7. So, to reduce these fractions, 24 over 25 is 0.96. 7 over 25 is 0.28. And 24 over 7 is going to be 3.43. 3 since we're rounding to the second place. All right, so these other problems you guys need to do on your own with a calculator, and it should be pretty straightforward. So you're practicing here, making sure that you guys are basically getting your fractions in the proper order, okay? Adios.